time to discuss at the end this time. All the other lectures we always ran a bit over. Let's just recap what we've done. On the first day, we learned a little bit what convection is and what it does. And we emphasized the role of organized convection, things like that. The second day, we learned that how we parameterize convection. And we saw that this mass flux approach is basically what everybody's doing these days. And we told you where this is coming from, what the theory behind it is. We learned about quasi-equilibrium as an idea which people use. We found out that most convection schemes determine the strength of convection that through a so-called cape closure. So they look at cape and from that decide what the strength of convection in the model should be. Now, this morning I showed you observations of convection that actually, if you paid attention, contradicted quite a lot of the things that people do in the models. Okay, so the observations didn't necessarily match the ideas in the models. We saw that grid area mean precipitation, convective precipitation is actually not very strongly related to CAPE at all. And so therefore, if you wanted to estimate it, CAPE might not be the variable you want to use. It was much more strongly related to convergence and vertical motion in the atmosphere. We also found out that, on the other hand, the intensity of the convection, how much it rains at a point, was very much related to CAPE. And already prompted by a question by Partha, I was already saying that maybe this idea of having the area of convection and the velocity combined into the mass flux and only working with this mass flux variable turns out to be a bad idea. Because half of it is interacting with the atmosphere in one way, the other part of it is interacting with the atmosphere in another way. So what I'm going to present now is how we are thinking of improving cumulus parameterizations. And I specifically don't want to talk about a new parameterization, but a new framework for parameterization. Because there's lots of things that we haven't really worked out yet, and we're really at a stage where we would invite lots of people to share ideas and try and use this framework to work with us and others to just try and make these models better. This is a direct copy of a talk I gave at ICMWF. So the beginning is a little bit repetitive, but I think it's good for you to hear it again. All right? So first of all, to understand what I'm going to talk about, we need to understand what convection parameterization is trying to do. And you know that because you spent the last 2.5 days here. But let's try and boil it down to a few slides in a nutshell, just to remind ourselves and keep that in the back of our heads for the rest of the lecture. The first assumption that we are making, and it's not entirely justified, especially not at very high resolution of the models. At coarser resolutions, it's more justified, is we postulate that we can divide the world into means and fluctuations. Okay, and we simply postulate that we can do that. So we say the pressure, the temperature, the wind at any point in a grid box, and here's a grid box with convection in it, can be written as the mean of that grid box and the deviation from that mean anomaly. Okay, so we postulate that we can do that, and of course mathematically we can do that. Then we say, okay, if we believe that idea, and we went through the exercise of deriving this on Monday, if we believe in this idea, the equations that we use in our models we can divide them into two parts. One becomes the resolved part, so that's the bit that the dynamical core of the model is trying to solve. And then there's a subgrid scale part. So there's a part that is not resolved by the model. And we saw that actually that has horizontal fluxes, which are neglected in all models. They have subgrid vertical fluxes, which is something we spend a lot of time on. And we have source terms, which is also something we spend significant time on talking about. So the parameterization task then is to describe the subgrid vertical fluxes and the source terms according to the processes that we want to describe. In our case, we were worrying about convection, of course. So then the next assumption that we are making in parameterization is somehow we can relate these fluctuations to the mean state. And the most traditional way of doing this is in turbulence closure, where you say the turbulent flux of variable S is related to the vertical gradient by some constant. And then this constant isn't really constant, depends on stability, all sorts of things. But it's this very simple idea that this fluctuation is related to the mean. In convection, we spend considerable time deriving this idea of representing this flux through a mass flux formulation, where we ended up saying this flux is a mass flux times the variable inside the cloud minus the grid mean, and this mass flux was a product of density, the fraction that's covered by convection, and the velocity in the cloud. Right? So that's how far we got. And of course we can see, and we learned this, that to make this work, we need to determine these variables inside the cloud, and we need to determine the mass flux. And we learned how that's done. We have cloud models, and we initialize them as trigger models and what. All right? So that's parameterization in a nutshell. I did tell you this, but I want to repeat it. So it's tempting to interpret parameterization as the physics of a cloud or an updraft, because we often end up with one equation for updrafts. And I just want to remind you, in reality, really what we're trying to do is not to represent one cloud in our grid box, but we're trying to represent statistics over all the clouds in the grid box. And that has consequences as to how we formulate our parameterizations. So parameterization necessarily, and you will see this very much in our approach, has to be a combination of statistics and physics, right? So if you get too physical about your arguments, you're losing track of the fact that you're not treating a single cloud. If you get too statistical about the way you do your parameterization, you may lose the physical processes that are crucial to have in your model. So you need to find a balance between statistical thinking, what's the ensemble of clouds look like, and physical thinking, which is, yeah, if the ensemble of clouds looks like that, the heating profile can be calculated in this way. This is really important, and it actually leads us to where I want to go with our new approach. Okay. So this you haven't seen yet, but we've talked about it a lot. I should have shown it right at the start of the first lecture. So one question you might have is, well, how well does all this work? We've been doing this for 40 years, you know, even more, but sort of, let's say, almost 50 years, 1980 sort of was when the GCMs became mature. They emerged in the 70s, so much earlier. So how well does all this parameterization work? How well do the models do this? And the answer is not very well, really, actually. Embarrassingly badly at some level, given how long we've been trying. So this is the mean rainfall error on the left-hand side of all the CMIP5 models. And they're big blue blobs here, and these numbers are large. So there's, you know, up to 50% error in the mean rainfall over many decades compared to observations. And you can see that the largest errors, not surprisingly, are in the regions where in the real world we observe tropical convection. You guys are very poorly off. There's a very large error that no one likes to talk about. Everybody obsesses about the Western Pacific, the cold tongue, the double ITCZ. But there's as large an error in the models in the Indian Ocean, in the Western Indian Ocean. And actually, we've been studying this error for a while. It's quite a hard one to pin down what's going on. And there's equally large errors in the Atlantic. But most people, because the way that we plot the maps, the Pacific is in the middle, everybody obsesses about the Pacific. And of course, El Nino happens there. It's a big phenomenon that affects many places. So this is for the mean state. The models don't look very good. Well, you might say, well, okay, who cares about the mean state as long as the weather in the model is right and the variability. So here's a graph of how well models do intraseasonal variability. So there's Kelvin waves here, there's the MJO is this blob here. Don't worry too much about what this plot is. The only thing you need to worry about is how, so this is the observations and all these other things are models. And the question you may have is how good are the models? How well does this plot look compared to the model, to the observations? And And there are a few models that look half decent, but most of them look pretty bad. All right, and don't try to find your favorite model here. Doesn't matter. This is just an example of the models not being able to reproduce the tropical variability either very well. So it's not, we're not as good as we would like to be with these models. Okay. So convection parametrization is usually what is blamed for this, and so we are not happy with the overall model results. But maybe we should also think about, from a physical understanding of convection point of view, we've moved on since the 1980s. I showed you lots of nice new results this morning, where we learned a lot of things recently about convection and how it works. So even at the process level, we can't be satisfied with our parameterizations. And here's my reasonably long list of things that I think are wrong with convection parameterizations at the parameterization level, not at the overall model result level. First of all, parameterizations all assume that you can either have shallow convection or deep convection at any given time step. All right. Well, we've seen, you just have to look at this picture, and it's not particularly chosen, that can't be possibly true. Because here's deep convection, and all around it is shallow convection, and even sort of progesticity type convections happening around it. So this assumption that you can only have one or the other is unlikely to be very good. We've seen in several parts of the lecture series how important the organization of convection is. It changes everything. It changes the heating structure of the convection, changes how it transports properties around, it changes the amount of rain that falls, it changes how long the systems live. And yet there's not one GCM on Earth that has a good representation. Most of them have none. One or two have some sort of half-baked things that they try and call organization, but no GCM can do this, can represent. And yet we saw half the rainfall in the tropics comes from organized convection. We saw that this morning, right? So half the rainfall comes from this, and yet we don't represent it in our models. That should worry us, I think. The relationship between the large and the small scales are assumed to be deterministic in pretty much every convection scheme that is around right now. You may have heard or read about stochastic physics, but that's usually bolted on after the convection has done something. So that's what that says is that if you were to walk around the Earth many times and you found identical large-scale states, let's assume we could do that, right? You take measurements and you find identical large-scale states. The convection schemes would predict that the convective state that goes with that large-scale state is always the same as well. Now, who in this room believes that the real Earth works like that? I don't. I don't think that's how the real Earth works, right? So there is a degree of stochasticity in the relationship between the large and the small scales, and that's not represented in models as well. All convection schemes, almost all, I think 95% of them, are local in space and time. That means at every grid point, at every time step, we pretend we don't know what happened in the previous time step, we don't check what happens in the grid boxes around us, we determine the state of convection diagnostically every time step. That's kind of bad because we're losing information, right? So if we already had convection in the previous time step, that's information. It's also therefore very hard to advect convection around. There's no propagation of convection with the mean flow. None of this can be represented in current models. So that's not very good. We already talked about microphysics and the dilemmas that that brings. If you have poor microphysics in convection and fancy microphysics in your stratiform cloud, as you increase the resolution, once you switch convection off, you switch over the microphysics, no one talks about it. And we also have no physically justifiable way to run the same convection scheme in different resolution models. The way people deal with this, the most common way is if you have cape closures, and people do, they change this time adjustment time scale. And they make it shorter as the resolution increases. But that's just cooking, actually. It really is. It's because the vertical motions in a grid box get larger as the grid boxes get smaller. The convection needs to react to it faster. But that doesn't mean in the real world that the real world works like that. It's just if you don't do it in your model, you get grid point storms and things like that. So there is no, it's not physically justifiable. We do it because we don't know what else to do, but it's no physical justification for this K time scale becoming shorter as the resolution goes to higher and higher, to smaller and smaller boxes. All right, so the question is, then can we, what have we learned from the real world? We went through this morning, so I'll be reasonably quick with that one. One iconic plot I think that I showed you this morning was that we've learned from the real world that the area average rainfall rate in a convecting atmosphere is largely related, strongly related to the area fraction that's covered by convection, not to the intensity of the rainfall. So the number one control on how much it rains in a box is how much of the box is raining. So in mass flux speak, that means this sigma, this area fraction, is very important for how much convection there is in a grid box. So it might be a good variable. I'm bringing this up because we'll later look at how to predict it in a model. That might be a good variable to go for to describe convection. We also learned that there are several types of convection that we need to take into account that behave slightly differently. This morning we identified 3 of the precipitating ones, and we know there's a 4th non-precipitating one, shallow convection, which we can't see with our radar, so I won't go into that again. Basically, we saw there's a congestus type, which has sort of medium rain rates, small to medium rain rates, where the rain rate increases as the depth of the cloud increases. We have one we call deep, where we basically, the rain rate is constant as the depth of the cloud increases, and then we have this really heavily precipitating overshooting time. Now, then the other thing, and this is the plot I promised I would show you and haven't shown you this from this morning, is we know what the relationship between, to make a parameterization, we need large-scale variables that tell us something about the small-scale state. If we can't find any, we can't parameterize. Okay. So then the question arises: what are the best large-scale variables? What's the best large-scale variables to use to describe the small-scale state? So what we've done in this figure, and you can read this up in a paper by a Dutch student, Jas, in 2015, is we've taken the convective area fraction, which, as we know, is strongly related to the grid mean rainfall, and we correlate it with 3 large-scale variables, and we do a lag correlation. So here's lag 0, and then -1 day to +1 day. Okay, so we do a correlation. How well is the area fraction correlated with stuff? And stuff is vertical velocity in the red, cape in the black, and relative humidity in the green, which is very hard to see, so I apologize. But you need to teach your students not to make green lines. Green lines you can't see on a projector, right? Too late for this student. He's often working by now. Anyway, so what do we see? So the first thing we see, let's start with cape, since we've talked so much about cape. The correlation of convection with cape is very weak. You can see that the largest correlation is the cape is leading the convection, so that's kind of nice. So it makes it look like it's a useful predictor, but quantitatively it doesn't explain. It explains 1% of the variance, right? Correlation is 0.1, 1% of the variance. If you square this, that's what you get. The next one we could look at is relative humidity, mid-tropospheric relative humidity. So it's relative humidity about 600 hectopascal. And we can see the correlation is actually higher, but it's the other way around. The relative humidity is lagging the convection. So this sort of tells us as once convection happened, the relative humidity in the atmosphere goes up in the mid-troposphere. That shouldn't surprise any of us, really. But again, the correlations are relatively weak. And then we see that there's a very strong correlation with vertical motion, but the vertical motion lags the convection as well. So this indicates that the convection may be causing the vertical motion rather than the vertical motion causing the convection. But even with lag correlation, one has to be careful. So now we can get into a really lovely philosophical argument, right? Sort of, the convection is causing the vertical motion, so therefore you can't use vertical motion to predict the convection. The good news was this student was a mathematician. didn't know anything about physics, he didn't know anything about convection. And he opened lots of people's eyes, because when he gave talks about this, they always bombarded him with, oh yeah, well, you can't use it because it's cold, right? And he said, excuse me. And I repeat his argument because I like it. He said, excuse me, I know nothing about the process that's going on. All I'm being told is I need to predict this cloud area fraction at time 0. Okay, that's my job. My job is my model needs to predict this cloud area fraction. Now, if I look at the 3 variables at time 0, which one would I choose to make that prediction? I would choose the one that has the highest correlation, right? And even though that has an even higher correlation later, the highest correlation right now is with vertical motion. So I will use vertical motion. And you can tell me whatever you want about physics. That's where I have the strongest predictive skill, very likely. The physics of this is of course more interesting in that I think what happens really is you get convection going that there is no one or the other. There are situations where you get a large-scale convergence or a mesoscale convergence and convection will follow. And then there are occasions where you have convection and that induces a circulation which leads to convergence and then convection will get enhanced. However, and it's kind of pointless to get into a big argument about which one leads which. I think the key thing in the evolution of convection is that you get from shallow clouds which are surface driven, you get some deeper clouds that generate heating, that heating generates convergence and that allows the even deeper clouds to go. So ultimately for deep convection, for really deep convection, vertical motion is a really good predictor, I will claim. And I have evidence for that, as you know. This graph I've also already showed you this morning, so let's concentrate on the bottom left part again. This is vertical motion scaled from downward motion to upward motion, left to right. Dryness of the atmosphere, so from moist at the bottom to dry at the top. And the contouring is the convective area fraction. This is from observations, from radar observations. And we see that we have a very sort of diagonal relationship as the atmosphere gets more ascending and dry and moister, the area fraction with convection, and hence the convective rainfall are increasing. And we see that there's a stochasticity to this relationship. This is the standard deviation of area fraction in each of the bins, expressed as a percentage of the mean. And we see the largest standard deviations are when the atmosphere is dry and not very strongly ascending. Whereas when it's very strongly ascending and moist, the relative noise in the problem is small. So we discussed that at length this morning. This also holds at another site. So this is the Darwin site, this is Kwajalein, there's a radar there where we derive the same things. The difference is that the Kwajalein site is purely oceanic and the large-scale forcing is much weaker. So you see we never get to these very large vertical velocities or very moist atmospheres at Kwajalein. It's much more bubbly background type of convection. We can derive mass flux profiles from observations. We discussed that this morning as well. So there's a lot we can learn from that. We can see that there's a small contribution to mass flux from congestus clouds. The large contribution comes from the dotted lines are deep convective clouds. And then there's a significant contribution coming from these overshooting clouds. And we see that that comes through different mechanisms, that the overshooting clouds actually have very large velocity but small area fraction, whereas the deep clouds have large area fraction but smaller velocities. So there's different mechanisms lead to the contributions from these clouds. All right, now can we use all of that? So given what we know models can't do very well, given that the things that we are unhappy with at the process level, is there anything we can, and given the observations have told us lots of new things, can we use this to at least start thinking about a new way of dealing with convection? And here's how we do it. By more or less coincidence, there was a development in the applied mathematics community where Guolem Koida and Andy Maida and colleagues have developed a toy model. For them it was really a toy model of tropical convection. And the toy model works like this. You have a box, and you can think of this as a GCM grid box, and I want you to start thinking of this as a GCM grid box. They didn't think of this as a GCM grid box. It was just a toy model. But
for us, think of this as a GCM grid box. And you divide your GCM grid box into smaller boxes. So let's say, this doesn't quite work out, but let's say this is 100 by 100 kilometers. Let's say we make these small boxes 1 by 1 kilometer. If they did in this plot, we couldn't see anything, so let's just live with the fact that they are. Or if we have radar data at 2.5 kilometers, from which we want to train this model in the end, let's think of each of these little boxes being 2.5 by 2.5 kilometers. It doesn't matter order of a kilometer, right? Then what this toy model does, it predicts the state of each of these little boxes. And there's, in their model, there's 4 allowable states. A box can be clear. A box can be a congestus cloud, has congestus clouds in it. It has deep convection in it, or it has stratiform clouds in it. Okay, so that's the basic premise of the model. And now you have to, what you do is you can condition your prediction on the large scale state. And that's what they do. So the mathematical technique that's being used is conditional Markov chains. So you use these so-called Markov chains. All that means is at every time step in your little toy model, you're predicting the probability that a state transition will occur at one of those little cells. Okay? What's the probability that one of those cells makes a transition? And that probability you can then convert that into a rate of transition, and that you need a time scale over which you want the transition to occur. That time scale, you can have some physical arguments. So for instance, this is the transition from clear sky to congestus. Okay? So we know it takes about half an hour for a congestus cloud to grow from nothing. So we make that time scale roughly half an hour. This is the transition from clear sky to deep. So we know to go from nothing to a deep convective cloud takes maybe 45 minutes, maybe an hour, something like that. So we make that time scale longer. These funky things here are the large-scale conditioning on the... you don't need to worry too much about the mathematics. We've since changed the functional form of this to make it a bit more bouncy and jumpy. But essentially, you can have as many parameters as you like. In their toy model, they use 2. And you can say, I want this transition probability to be high when certain conditions are fulfilled and low when certain conditions are not fulfilled. In their model, the C stands for cape, right? And the D stands for dryness. So if the atmosphere has cape, but it's very dry in the middle troposphere, they increase the probability that you're going from clear sky to congestus. If, on the other hand, the atmosphere has cape and it's moist, 1 minus this, so that's the opposite condition, then we're increasing the probability that one of those little cells makes a transition from clear to deep. Okay? We have since changed this, as I said, so you can add parameters here. If you want more predictors from the large scale to go into your probabilistic model, you can do that. We've changed cape to vertical velocity since. And yeah, that's pretty much how it works. So then you have a probability that a transition should take place, and now you need to make a decision whether it should take place or not, given the probability. So what you do is you toss a coin. Of course, computers don't toss coins. It would be awfully noisy in the computer room if they did that all the time. So they calculate random numbers, right? So you calculate a random number, you compare your probability against that random number. It's a bit more complicated than that. Those of you who had to deal with nuclear decay in their studies, it works exactly like nuclear decay, right? So you have a probability of a state transition in nuclear decay, which depends on time. The time depends on the half-life. And eventually the atom will make its transition, and here our little grid box will make its transition. How well does this work? So we've taken this idea, and we've taken the toy model, and now we've taken our observations from Darwin and Kwajalein, which are at the top again, so you've already seen these figures. And we have tuned the parameters that the statistical model has based on those observations, half the observations, and then make predictions for the other half, basically. And this is what we get. So this is, these are the observations at the two sides. Let's focus on the Darwin side. This is slightly more interesting. And these are our model predictions. So this is the mean area fraction as a function of vertical motion and dryness. And you can see that we can in principle reproduce this diagonal evolution, so moister and more ascending leads to more convection, more area of convection. The fascinating thing is if you look at the standard deviations the model is producing, it actually produces the right shape of that as well. So the relative standard deviation is smaller when you get to the high forcing end and stronger when you get down here. Note that the scales are different, so it's not as good as this in terms of the noise.
So one of the reasons we later changed this functional form of this gamma function is because of this. Everything is a bit smooth in this model. And you can make it a bit more noisy and a bit more radically changing in time by changing the functional form of these gamma.
This is the CAM6, right?
Sorry?
This is a CAM6 or which model?
Well, this is just an offline version.
Okay.
So we'll come to implementing this in the GCM in a minute.
Okay. So this model, all we are showing is that some of the key behavior that we see in the observations we can reproduce with this Markov chain model. Okay, so that's all I want you to take from that. So it's likely a good model to make predictions of area fraction as a function of the large-scale state. Obviously, we only started using this about a year ago, or 2 years ago, so there's a lot of work to be done to refining what the large-scale parameters should be, what the timescales should be, what the cloud types should be that should be included. Even that's still a bit open. But it's giving us great hope, actually. So, now we come to what we want, where we want to be in 5 years. Actually, I wanted to be there much faster, but funding, with one postdoc, we'll be there in 10 years, actually. With 2, we might be there in 5. With 5, we could be there in 2. But there you are. So this is the new framework that I'm envisaging. And the reason I like it, or the reason we're proposing it, is because we think it can solve, in principle, in practice a lot of work needs to be done, but in principle, all the problems that we've listed. So here's what it looks like. Imagine here's your GCM. You have your grid. Here's your small grid, and we're using the stochastic multi-cloud model, as it's called, this Markov chain idea. And we have, for argument's sake, in this figure, I made 4 types of things that matter to convection. The black is deep convection, the purple is congestors, the yellow is shallow convection, and because cold pools are so popular, you can even include cold pools in this. And you now need to find rules to predict how many of these points, or the evolution of these little grid cells in time as a function of the large-scale state through those types of convection. Okay? So the stochastic behavior of convection was one of the things we criticized, is already built in. Because we're using Markov chains, we're throwing random numbers, the model is already stochastic. No further work required. We are already producing a stochastic realization. We're producing one realization of a stochastic process, rather than treating the problem deterministically. Easy. Coexistence of different types of convection, that's also built in. And now all that's left, and this is a hard choice, is A, to decide how many types of convection do you want to include. Okay. And the minimum that we are thinking we need to include is shallow congestors and deep. We are thinking hard on whether we need to include the overshooting as a separate one or not. We don't know at this point. So let's say shallow congestors and deep is kind of the minimum. But they will coexist, just like in this picture. We now have actually, I don't have any results to show you yet, but we have a version of this running, not crashing anymore, which is progress, right? When it's not crashing anymore, that's the first step. Organization is an interesting question. So can this model do organization? It turns out in its current form, it can't, because each of these little grid points is independent of each of the other little grid points. However, that doesn't need to be the case. There are approaches where you can refine this this Markov chain process by making the probability not just a function of the current state and the large scale, but also as a function of the state of the neighboring grid points. And the applied mathematicians are already on the case. They have already developed some of the mathematics for this. So in principle, in a few years, we will be ready to also implement a level of organization in this scheme, because we can align certain
convective points with each other. And once they are aligned, we can change the rules on what they do. Okay, we'll come back to that on the next slide. Finally, how do you deal with resolution awareness in a model like that? And can you? And the answer is you can, but it's a little tricky. So option number one is this stochastic model, you train it on some data or some cloud resolving model results, whatever strikes your fancy. But you will have trained it for a certain size grid. So we've trained ours on 150 by 150 kilometers. Now if you want to run the model at 10 by 10 kilometers, you can't use it because it was trained on 150 by 150. So what are you going to do? Well, so there are two choices. One that I don't like and one that I do like, and I have no idea whether either of them works. The one that I don't like is you can retune your model for every resolution that you have. I don't like that at all because it's not very attractive to me as in terms of how to build a scheme that is really smooth and makes smooth transitions and stuff like that, because then every resolution needs its own set of parameters for the statistical model. Not very attractive. However, the other thing you can do is you can say, I don't care if you run a 10-kilometer model. I will average the output from the 10-kilometer model when I get to convection to 100 by 100 kilometers or 150 by 150. Then I'll run my stochastic model. And I can do that because the stochastic model is prognostic. It already knows where the convection is, right? From the previous time step. So it's not starting at the very beginning of the run, it spins up. Well, that's lots of things spin up at the beginning of the run. But then it already knows where the convection is. So I'm going to aggregate all my grid points to say 100 by 100 kilometers. I run my statistical model, and then I give the information that the statistical model produces back to the 10 by 10 kilometer model, or the 5 by 5 kilometer model. What's really, really nice about this is, as you can imagine this becomes your 10 by 10 kilometer box, this one here. So a few grid boxes here get put together to the 10 by 10 kilometer box. What happens is the area fraction with convection in that 10 by 10 kilometer box is now 1, or very close to 1. What you do, at this point you can dynamically decide, objectively, without any interference, that at that grid point you don't need to run the convection scheme. The large-scale scheme should be able to take care of it. Whereas over here, where you have only one convective point, the area fraction may be 0.2. And you say, 0.2 is still pretty small, I'll run the convection scheme. So rather than having to make a hard decision at the beginning and say, well, the model is 5 kilometer resolution, let's switch the convection off. Or it's 5 kilometer resolution, we better leave it on. You don't have to do any of that anymore. The model will decide as it runs, as what is the area fraction in my grid box. If it's large, I'll switch the convection off. If it's small, I run the convection scheme. So that's also, if it's shallow convection that I find in my grid box, I'll run the convection scheme. If it's deep convection, I may switch it off. Stuff like that. You can do all that in principle. I have no idea whether it's going to work, but this is what we are pursuing at the moment. This is how we want to do it.
So, how does it address your memories?
Oh, the memory is addressed very, very simply. The whole stochastic cloud model is prognostic. So these grid cells, once the grid cell is deep convection, the next time step it will still be deep convection unless there's a transition rate that says it should die. And even if it should die, it won't die in one time step. The number of cells will reduce probably because you flip a coin. Some will die, some won't. So it will give a much smoother evolution of convection. We actually know that it does give a much smoother evolution of convection. Right?
And it's scale aware by default, right? You say.
Well, the way I want to implement it, it will be scale aware by default. Yeah. As long as you make to make it scale aware to the very end, what you need to do though is you need to have these little grids need to have a physical scale attached to them, which in the toy model of Coida and MIDA they don't. There's no physical scale attached to them, they're just little boxes. So we are thinking of having an order of 1 kilometer. It depends on the data that informs the model. If that's 2 kilometer resolution, then you may get away with 1 kilometer, making this equivalent to 1 kilometer. Alright, so what do we do in the vertical then? So if this works, the end result will be at cloud base, we will know what the area fractions of the different types of convections are. So we know half the story of the mass flux, right? the sigma. And we don't know it for just one type, we know it for many types. The reason I like to call this a framework is if you feel you want to make more cloud types, shallow, congested, and deep isn't enough. You want one for every model level that you have, which is basically what Arakawa and Schubert did. You can do that too. You know, it's a framework in the sense you can do whatever you like. You just add more cloud types, but then you need more rules that describe how this cloud type evolves, given the large-scale state conditions and its history. That's two things it knows. It knows which state it's in right now, and it knows what the large scale does. And from that, it needs to decide what happens next. Okay? So you can have as many cloud types as you like. The next thing is also, we now need to apply a cloud model, right? So we have the area fraction, we need the velocity, and then we need to transport everything up in the vertical. So we need a cloud model. And the question you may have is, how many cloud models do you want to run? And again, you have lots of choices. You could run a cloud model for every little grid box that has convection in it, and make it always slightly different to get a sort of ensemble representation. We are thinking at the moment we will run one cloud model per type, per time step. So we will run one for shallow, one for congestors, and one for deep. So that way, instead of running one, which is what we're doing now with the bulk mass flux schemes, we will be running 3. But you can run more if you think you want to give more computer time to this problem, which it deserves. It's a big problem. Why should all the radiation guys get all the computer time? Radiation guys and the microphysics guys. They get all the... And convection, you know, keep it simple, people. It's too hard. It should better not take much time to calculate. Why? Why you got the radiation people get all the fun? No. That has to stop. All right? So convection people need some computer time too. So anyway, you can do lots of things. So in the vertical, all we are envisaging doing is actually then you need to apply a cloud model. And as I said, you can apply it per type, per grid cell, whatever you would like to try. It's even more fun because you don't need to use an entraining plume model, which is why this is a framework. We will start with an entraining plume model, which is what we've discussed the last 2 days. This is one of the cloud models that is in use in mass flux schemes. And because we already know how to do that, that's how we start. But if you come along and say, I really hate entraining plume models, and clouds aren't entraining plumes, they are bubbles. So I'll write a bubble model rather than, people have done this. You may think this is crazy, but no, people, you know, if you look at clouds from a distance, they look like bubbles going up in the air, don't they? Not like plumes that go up. So some people have argued entraining plumes is terrible, and you should be using bubbles. So you can do that here. So we will use entraining plumes. And in the initial implementation, it's really, really simple. We have the area fraction, the vertical velocity we can calculate. I showed you the trigger function that we developed for the ECMWF model. That actually calculates vertical velocity at cloud base, right? So it's very simple. So there you go, we have it. In the first implementation, I will show you results from, we did it in an even simpler way, which I'll come to. And then you multiply the two together, that gives you the mass flux at cloud base, and then you do an updraft calculation and a downdraft calculation, and all other calculations we already know how to do for each of the types. So you end up with, say, 3 calculations instead of 1. We think that will be the best compromise for immediate progress, and then we can become fancier in the future. Will this work in a GCM? Well, my answer is, I don't know, but I am very hopeful. And why am I hopeful? It's because we've already done some work, of course. Carsten Peters, this came out in James this year, has taken the simplest version of this idea and put it in a GCM. The simplest version of this idea is we only use one type of convection, only deep. So forget about congestors, forget about shallow. So the shallow convection we leave to whatever the model did before, we don't change it. But for deep convection, we change stuff. And the only thing we're going to change is the closure. So we're going to leave the deep convection scheme alone. However, when it comes to calculating how much mass flux is there, we're going to run this model in the background. It will always run in the GCM. So for every grid box, we will know what the deep convective area fraction is. We will assume, and this is kind of fun, that the vertical velocity is 1 meter per second, which is a very good approximation. It's somewhere between 0.7 and 1.3. It's probably not a good number over land, where it's more like 2 meters per second from observations and cloud models. So if you see bad results over land, that might be because we've chosen one. And then we'll put that in the model and we'll see what happens, right? So that's what we did. And here's what happens. Let's start by looking a little bit at the process level what happens, because it's really, really interesting. On the left, top left, this is the mean updraft mass flux when there's convection. And it has 3 types, so the only one we are interested in is the blue one, which is deep convection. So that's, what is the mass flux when deep convection is present? As a function of height, or is actually pressure. Okay? So you can see the control model is this dotted line, and our new model is the blue line. So the first fascinating thing that we are seeing is that when present, the mass flux is about 1/3 of what the previous model gave. Now, initially I was quite shocked by that, and I still am somewhat shocked by that. But we know ours is using observations to come up with that number, because this area fraction, the one thing we can really observe really, really well from radars, is the area fraction of convection. The velocity, less so, but we don't use the observed velocity in any way, shape, or form. Partly it could be because we chose 1 meter per second, but even if we choose 1.5, we only, then we increase it by 1.5, but not by 3. And it's not 3 meter per second in cloud base, that we know. And so my conclusion from this is current models completely overestimate the mass flux when present. Just too much mass is being pumped through. The other thing that I immediately realized is that, of course, we're only using one cloud type at the moment, and in the future there will be other cloud types coexisting with this. So the mass flux at cloud base will go up, because this is the mass flux for the deep convection. But then there will be shallow convection, and that will have some mass flux. There will be congestus, that will have some mass flux. So the total mass flux will be larger. So we're missing that. However, remember, because the current model has to choose between deep and shallow convection, this is the mass flux it puts into the deep. So it's entirely possible that this overestimation, so I'm convinced now that current models overestimate mass flux when present. So when convection goes, it's too strong in current models. But the reason it might have to do that is because it doesn't have the other cloud types present, right? It might not have shallow convection and congestus, but it needs to maintain some sort of equilibrium in the boundary layer, so it needs to pump out mass of the boundary layer at a certain rate. At any rate, so one of the big changes we are making with this new scheme is we are reducing the mass flux when convection is active. It's much weaker convection. This is the PDF of mass flux, and there's something very curious. So the blue is the control model, and the red is our model. So our model has this real exponential decay here. Large mass fluxes are rare and small mass fluxes are common. The control model has a really funky PDF. It peaks at 0.02, so it has a favorite value, as you can see. And then it has a second favorite value here, and then it has this almost sort of bimodal, and it's larger than what we get from our model most of the time, right? So you see all this tail here. Is much larger. But surely there is no favorite value in the real world. I'd be very surprised if the real world had a favorite value of convective mass flux. It's very unlikely. We got some really nice results without trying very hard. So this is the lag autocorrelation of daily total rainfall. The blue is the control model. Now black is observations, because we have daily rainfall observations over the tropical oceans. And the blue model had too long an autocorrelation, and ours is behaving in a much better way. What about these plots that I showed you earlier? Well, unfortunately, we don't solve everything. So this was our frequency wave number spectrum of OLR, so giving us an indication of tropical variability. Remember, these were Kelvin waves. This block down here, this guy here, is the MJO. The control model, Max Planck model, very famous model, no MJO at all, no Kelvin waves at all, way too much power in the westward propagating part of the spectrum. Our new model improves on this pretty amazingly pretty well. It's far from perfect, but at least we have some Kelvin waves, we have a hint of an MJO. Other MJO diagnostics we've done, which you can find in the paper, show it's actually quite good. And here's one of the surprise results.
which is, I think, is my last slide pretty much, close to. So don't despair. This is a plot of a different way of showing the result I showed you this morning, which is how is rainfall related to humidity in the atmosphere. And this is from ERA interim, and for humidity, the vertical axis is pressure, the color is relative humidity at that pressure level, and the x-axis is the amount of rainfall. So we're going from no rain to a lot of rain over here. Okay. And what we see is that when it's not raining, this is for the tropics. When it's not raining over the tropical oceans, the middle troposphere is dry. The lower troposphere can be moist because we're near the ocean surface. And the high rainfall rates go together with very moist atmospheres. Okay. Models are notoriously bad at representing this. As you can see from this Eckern control model, it makes a lot of rain. It makes larger rain actually than observed in very dry middle tropospheres. And that's not what's observed. The atmosphere doesn't work like that, but models do work like that. And because we have this explicit predictor, dryness will stop deep convection, by definition our model must obey this to better, right? It's built in. And of course we get that. That's not the surprising result. When we sent this out the first time, one of the reviewers said, okay, so you get a better MJO. Do you get a better MJO because you have this moisture relationship right? Which is sort of, a lot of people talk about the MJO as a moisture mode, and blah, blah, blah. And they say, oh, you have to have this moisture relationship correct to get a good MJO. Otherwise, you will not get a good MJO. And, or is it because something else you changed, like your mass flux is much smaller, for instance? So they didn't accept the paper, which we were very angry about initially. But then we were very happy about afterwards. So it's a lesson for the young folks in the room. Sometimes, when the reviewer asks for major revisions, you discover something even more exciting, and you're trying to address it. So don't despair when someone asks you for major revisions. Go and do them, because there can be some cool stuff coming out. The cool stuff that happened to us is they said, no, is it the weaker mass flux, or is it that moisture relationship? So we said, oh, let's do a few more experiments. I don't have results here because I didn't bring them. I tried to find them this morning, I couldn't. So I just tell you, and you have to believe me, you can go to the paper. So what we did is we did an experiment where we took the old scheme and divided the mass flux by 3, right, to make the mass fluxes closer to the new scheme. And then we also did an experiment where we took the new scheme and multiplied the mass flux by 3 to make it closer to the mass flux of the old scheme. And what we found is that we then analyzed the same plots as here for all these experiments. And what we found is that if you divided the mass flux by 3 in the old model, this moisture relationship was just as bad as it was before, but the MJO was very good. If we multiplied the mass flux with 3 in our new scheme, the moisture relationship was just as beautiful as it was here, but the MJO disappeared. It was much weaker. So actually, this MJO being active or not in the model had nothing to do with this moisture relationship. It had everything to do with how much mass flux your convection scheme was producing. We do not 100% understand this, but it's consistent with lots of other results actually. For a model to have a good MJO, you don't want to do a lot of convection. The less convection you do, the better the MJO gets. People have found this. The very first study was Wang and Schlesinger in 1919, I think. They used a 7-layer simple climate model with 3 different convection schemes, and they made it easier or harder for those convection schemes to trigger. And they found that the harder they made it, the better the MJO got. But no one has found anything new since, I believe. We've done lots and lots of studies with models, but every experiment that's done leads to the same conclusion, even though people often don't write it down. That is, the less convection you do in your model, the better the MJO gets. The more you leave to the large scale to do, the better the MJO. What happens frequently, and didn't happen in our model, and that was something we reported in the paper as well, is when you do that, switch the convection, make the convection weaker, you get better MJO, your mean climate gets worse. But that didn't happen for us. For us, the mean climate did not get worse in all these experiments. It was roughly the same. So that's good news. So
So we have found something interesting that we don't fully understand. Right. So I'm leaving you with something that we don't understand, which leads me to a nice little anecdote. When I started in the field, my boss was Michael Tietke convection scheme. He was my first boss in the field. And he said, listen, when you give a talk, every talk should have 3 parts. And it's something to learn for the young folks. Each of your talks should have 3 parts. The first part should be everyone in the audience can understand it. All right? So you should pick, ask yourself who's in the audience, pick something that you know everyone in the audience should understand. The second part should be about you and the experts in the audience can understand. And the third part should be something that even you don't understand. It's very, very good advice, because if you have something in your talk that you don't understand, you may have an interesting conversation with someone in the audience afterwards. If you understand already everything, you will not get much out of giving that presentation, right? The audience will, but you won't get anything back. So always put something in your talk that you don't understand. So I put something in the talk that I don't understand. So we are currently implementing the multiple updraft version of this. This is the last slide, and I don't have results yet. So we use the icon model now instead of the ECA model, which was the previous generation of Max Planck models. And we have 3 types. We are assuming 3 types of convection: shallow, congestus, and deep. Shallow we do very simple. We assume a constant fraction of 0.03, which is backed up by LES results. As a first attempt, that's good enough. It's not what we will do in the long run, but for starters, it's good enough. And the congestus and deep fractions we predict using this stochastic multi-cloud model. It's early days, but it's no longer crashing, so we can start looking at the results, and we are. Thank you very much. That's all I have to say, and thanks for being such a nice audience for the last 3 days. All right, let's have a chat. Questions, discussion, concerns, solutions.
Okay, in a way, you said vertical velocity plays a major role in deep convection.
Yes.
Isn't that what 40 years back Pune was also saying in British convection, parameterization of it? And so are we coming a full circle in a sense that we are going to use it if at all we are to use it?
No, actually, what I'm saying is vertical velocity. Is that what you mean, vertical velocity?
Vertical velocity.
In the.
I'm just looking at your correlation and saying that's the best thing.
Yeah.
Even if it is the peak is at a little
I
later,
think,
but there is still significant correlation. So if you are going to use a kind of a diagnostic parameter, predict
So one difference to Kuo is he did everything on the moisture budget and emphasized moisture convergence. And I don't think that's necessary. I don't think it's about the moisture. It's about the convergence. It's about the dynamic field. It's about the uplift, the cooling that comes from that. So the moisture part, we are not doing a moisture budget here. We're using it in a different way, but conceptually you're absolutely right. And I predict convergence is going to make a big comeback as the variable to use to look at the strength of convection. That's my prediction. It was Kerry Emanuel who killed it, who said, oh no, you should never look at moisture. Moisture is not important. It's the energy, and energy is represented by K. And I agree that moisture isn't it, but the convergence is. Convergence is really very important. And so, yeah, I think there's going to be a comeback.
Yeah, especially if you're looking at monsoon. Over land, if you don't have convergence, and even moisture convergence, there's no way it can sustain.
Exactly.
So, it has to be, moisture convergence has to be a basic feature for any convection, especially over deep, like if you look at Indian monsoon.
I agree. I think there's the dilemma that we're all facing is that we are going. Shallow convection is a completely turbulence-driven process. There's no dynamics interaction. It's kept by an inversion, and the dynamics controls that inversion, but it doesn't interact. Deep convection is highly interactive with the dynamics, right? And I specifically use the word interactive. It's not one way or the other. They are coupled. It's a dynamically coupled phenomenon when it's raining a lot. And for those of us who don't believe that, I think I said this before to you, if anybody ever challenges you on that deep convection is highly dynamically coupled, ask them where the water for 20 millimeters a day rain is coming from. And if they tell you it's coming from the surface, you can laugh at them. Because surface evaporation is 3 to 5 millimeters a day. The only other option is it could fall out of the atmosphere, but then we would observe a drying of the atmosphere from 60 millimeters down to 40 millimeters, which we never do. It always stays, the moisture always stays the same. So where's the moisture coming from? It's coming from convergence. It has to come from convergence. And everywhere where it rains a lot, there is convergence of moisture. It has to be. There's no other way. You can't sustain, as you said, you can't sustain rain. So,
Okay,
yeah.
Second question is, when you're saying you're going to have different types of, in a subgrid,